Hey, I want to talk to you tonight, guys, about and girls, about the origins of periodic insect outbreaks. And given the audience, I specifically want to take a historical perspective and a geographical perspective. Um, I want to show how my thinking on this subject has evolved over the past 30 years and how I've had to actually personally struggle um, with my early emphasis on elegant formalism behind periodic insect outbreaks, exemplified by the left-hand side of this graph, the British school, and Tom Rayama's approach to spruce butter and population dynamics modeling, his elegant theoretical work and his rigid formalism, versus what I learned later on in life through my exposure to the UBC school, starting with my dissertation work on tent caterpillars in Alberta under Jens Roland. And I'll start with a quick little story about how I got into my dissertation program in '94 in Alberta, all cocky because I'd read Tom Rayama's Analytical Population Dynamics on the right. I understood the theory, the math. I felt pretty smart. And I remember studying for my candidacy exam, and I came across this U.S. Forest Service research paper by Robert W. Campbell, Population Dynamics of the Major North American Needle-Eating Budworms, and he basically said Royamo was wrong. And I panicked, and I remember distinctly slapping down the volume and kind of shuddering and wishing, hoping that my committee won't confront me with the contradiction between Royama versus Campbell, these two guys who didn't agree with one another. And I literally panicked. I had a panic attack, panicked and panicked. And I guess because I panicked, I survived. But what I learned on that occasion, it was the start of a great big journey to reconcile these wildly divergent views between the British school, the top-downers, exemplified by Royama, and the UBC school, the skeptical empiricists embodied in Campbell and many others. And I came to realize how powerful this dichotomy was and what a challenge it would be to reconcile these divergent viewpoints. So this is kind of a scary talk because it's a personal journey, really, and I'll try to be efficient with my time. But there's kind of a lot to cover, and typically I give really technical talks on population dynamics and modeling, and modelers love it, mathematicians love it, and entomologists, historians, and geographers don't, because I get in the weeds and I'm showing equations and explaining dynamics. I'm going to try to take a high-level view. I will get into the weeds a little bit, but I'll try to keep this high-level view. So on the left, you've got Sir Robert May, Nisbet Royama, and my master's advisor, Jacques Renier, who, although being First Nations himself and French Canadian, was nonetheless an advocate of the British School of Ecology. And so I've got a time arrow going from 1950 to 2000. But over on the right is this rich ecosystem of workers, thinkers, writers, researchers, experimentalists who had a different view from this British school. And the focus was really on hypothesis generation, hypothesis testing, models, yes, but models as they applied in the field under real circumstances, and a more inclusive consideration of all the things that are in an ecosystem, as opposed to the British school, which is like parsimonious. Let's get the mechanics working. Let's illustrate concepts. Let's focus on clear theory. The other guys were more kind of, I would say, more ecosystem oriented, more holistic. And the center is dominated by all Lepidopteran thinkers, but the right column, starting with Hector Allen Richmond and his Forever Green, when I read that book, it really spoke to me. And in fact, some of the data that he collected in the 1930s, I'll show, informed our understanding of mountain pine beetle outbreaks in British Columbia, which subsequently informed our understanding of mountain pine beetle outbreaks or the outbreak in Alberta. So this early work was kind of foundational to the success of mountain pine beetle management in Alberta. I won't be able to tell that whole story, but this is kind of an overlay where I'm showing all these different influences as they flow from the top down into works that I've published recently. Because I've been on this writing binge, because I was very confused, honestly, for 20 years. And it's only about 5 years ago that the light went on and I started making sense of what was going on in these complex spatial temporal dynamic systems. and how all these different systems were actually doing something quite similar qualitatively. They just differed in the quantitative aspects and in the parameter estimates governing population processes. So on the bottom, I've got six papers listed there on spruce budworm, forest tent caterpillar, jack pine budworm, a comparative paper, and then mountain pine beetle that really tries to pull together an integrated view of forest insect population dynamics um, across Canada. And what I'm trying to show you tonight is that the British school is a good start for kind of a simple understanding of ideas, but it isn't until you hit the UBC school where the rubber hits the road with data confronting models where you're forced to ask, well, what's really going on in these systems? And it's only when you start really peeling back the work of Judy Myers, Jens Roland, Neil Gilbert, Vince Nealis, Bill Wellington, Kenneth Watt, Buzz Halling, Don Ludwig, Bob Campbell, and my most recent collaborator, Brian Sturdivant, who's more of a forest landscape modeling guy. And then over on the bark beetle side, Hector Allen Richmond, Les Safranek, Ken Raffa, and then Alan Carroll, who I write with a lot recently and ongoing. So yeah, without the stuff on the right in the blue box, the stuff on the left with the red box doesn't make any sense. So our journey starts with the spruce budworm, and this paper by Yann Boulanger, wonderful guy, who in a 2012 paper talked about the remarkable stability of the spruce budworm outbreak cycle in southern Quebec. And this is very much in keeping with a Tom Royama's view of regular clockwork cycling. And moreover, I'll get into this a little later. It's also consistent with groundbreaking work from 1993 by Tom Swetnam and Ann Lynch from New Mexico on western spruce budworm on Douglas fir. These are tree ring studies, and they also commented on the remarkable stability of the 30 to 40-year cycle. So this is very much in keeping with the clockwork theory, Tom Royama's clockwork theory of forest insect population dynamics. And this is the bias that I took into my own work as an Eastern Canadian born in Newfoundland and raised in New Brunswick and educated in Quebec. I'm an Easterner. There's no question about that. So when I started looking at forest tent caterpillar in Ontario and Minnesota, this clockwork paradigm had some merit. And Lloyd Sapel in the 1962 paper used to actually number his outbreak cycles with Roman numerals, and he said this thing was a calendar, and you could actually count these things off with Roman numerals, which is very bold. And it also roughed against the Western Canadian entomologists like Hildal and Reeks in 1960, who said in the Canadian prairies, the forest tent caterpillar does not do this. And the Americans south of Minnesota are also disagree vehemently with this idea of spatially synchronized oscillations. And so when I started my dissertation research in 1995, this was my bias, my Bayesian priors. This is what I was thinking. And I ended up having to throw it in the garbage after 20 years of fighting with it. And I couldn't get it to work. And what I did get to work was the UBC school's approach to understanding complex spatiotemporal dynamic systems. Now, the clockwork theory, if you're a history buff, the clockwork theory actually goes all the way back to Huygens in 1673 in his La Phénomène de la Sympathie des Horloges, where this guy was building watches, and he was a physicist, and he was an experimentalist. And he had noticed that they were using clocks for navigation on ships. And so he noticed that if you have two similarly constructed clocks and you start these things off with different phases in the tickers, that the vibrations of the deck boards through the chairs on which these clocks were suspended, even if the phases started off differently, in a matter of less than a minute, these oscillators would come into phase with one another. So this is 1673, and it's the first idea that physical systems can be synchronized by very tiny random perturbations. So when the phase is free to be determined, then the period is the cumulative result of the sum history of all previous stochastic interactions, even though they're mild, they start accumulating. And so you get la sympathie des horloges. And so Tom Royama's idea, based on Patrick Moran, 1953, was that insect populations do the same thing. If they cycle, they can be synchronized. And so the source of the synchronization, i.e., the vibrating floorboards of the deck boards of the ship, is completely different from the mechanism that causes the oscillation, which is the pendulum on the clock. So this is an old idea, but it really got revived when Tom Royama wrote his book in 1992. This idea absolutely took off and turned it into a cottage industry, which I've been fighting against since that time. But when I started my dissertation in 95, I tried to make sense of the tink caterpillar system in Alberta, and I basically could not do it. I did my best. I got a number of papers out of my dissertation, I think 5 papers, but I didn't get the big one, the thing that made sense of it all, until 2023, because it took that long for the light to come on. And this is a result here from this paper that I did with Jens Roland, who presented recently in this series, or is presenting next week. I can't quite recall. But, I wanted to start this dissertation doing kind of modeling and theoretical ecology, the British school. And Jens said, no, I'm an empirical guy, and we're going to confront hypotheses in my lab. So if you're going to work with me, this is what I'm here for. So that's the track I chose to follow. And so it was hard because I was trying to take the British paradigm and apply it to real world data, but using the UBC, the rigid formula for experimental ecology, the UBC model. And so what I found was that the dynamics in this system were not simple at all, and they didn't conform with the clockwork theory. And I'm going to try to grace through this at a high level. You can go read the papers if you want to get into it more. But the left panel show these 11 frames, 11 time periods. So these are 11 different outbreaks in space in color on the left. And the red is where you're getting heavy impact, and the blue is where you get no impact. Alan, do you see my cursor when I move that around?
Yeah, we do.
It's great. So there's a heavy impact of an outbreak in this 1948 to 1953 window. And you can see that in the next frame, 1953 to 62, it's blue. That area that was red is now blue. So there's not much impact. And so what happens is that this is a tree ring based reconstruction of outbreak activity with the red as the heavy impact. Where you're getting heavy impact, this epicenter moves around systematically around the landscape. And in fact, the spatial correlation between successive frames is about minus 0.34, which is not consistent with kind of clockwork theory. Also, these epicenters are quite restricted. The outbreaks never cover the entire study area. They're just spots, and these spots are pulsing around. This is not consistent with clockwork theory. And when I first saw it, I didn't know what to do about it because it meant that something was wrong with Royama, and he was my god. He couldn't be wrong. So I had a problem. And it took me 20 years to figure out what the problem was. But I figured it out. The rest of the graphs basically explore the space-time behavior of this data series. And you can see that in the time series, sometimes you get these big growth declines, like in frame 4, frame 7, frame 10. But in a lot of the others, frame 11, 9, 8, 3, 2, these are very mild growth disturbances. And in fact, the peak distributions tend to be bimodal. You get intense outbreaks, but then you get these less intense kind of localized eruptions. So this bimodality is not consistent with clockwork theory, which is premised on the idea of a Gaussian distribution of cycle peak distributions. So there's some complexity here in the bimodality of the intensities that you observe. And spatially, if I take these impacts over here in these maps and I correlate them against the spatial impact of against the spatial distribution of host, where blue is lots of host aspen and red is not much host aspen, what happens is that the outbreaks are squibbing around. One outbreak will be in the continuous forest, but then it will go to the fragmented forest, back to the continuous, back to the fragmented. So this thing is moving around very dynamically. So the distribution of correlation coefficients between the insect and the forest is bimodal. Sometimes it's positive and sometimes it's negative. And that's also not consistent with clockwork theory, where these cycles synchronize. And the distance here involved is like 20 kilometers by 20 kilometers. So at that scale, there's lots of dispersal. The weather is identical across the grid, and yet the dynamics are not spatially synchronized. This system is fighting against all the forces of synchronization, and that's just not consistent with clockwork theory. And now I know it means that Royam is wrong. But proving Royam is wrong is a big deal to say that. So we have to move off the tent caterpillar system and move into systems that people really care about, not these model systems, toy systems in Alberta with Yents, with tent caterpillars. We have to get into budworms, a system that people really care about, which is doing the same damn thing. But it's a lot harder to prove, and there's a lot more data that you got to deal with. Okay, so this could be a long story, and I'm going to try to be efficient. But on three different occasions, I've tried to tackle this subject in '04 and 2012, but in 2024, I finally nailed it once I got the tent caterpillar paper out in 2023. I went back to time series like Boulanger and Arsenault 2004 in their study of spruce budworm tree ring data in eastern Quebec, and then his 2012 paper in southern Quebec. And in both papers, they talk about the remarkable stability, the remarkable periodicity. And the funny thing is that when you actually take these time series data and you try to build a time series forecast model, you get a forecast model that has incredible spread on it, incredible uncertainty. So there's not enough periodicity in this system to generate a robust forecast. Now, if this system was cycling synchronously, you'd be able to predict when the next outbreak is going to be and how intense it's going to be. But you can't do that. And the problem is that the intensities are bimodal. You get big outbreaks and you get little outbreaks. And they even tend to alternate between big, little for reasons we did not understand in 2004, 2012. But I'm going to show you what is regulating that. But we start with this observation that you can't do forecasting in this system, even with 400 years of tree ring data. So waiting 3 more cycles and getting 100 more years of data, you're not going to increase your forecast power. This is not a data limitation. There's complexity in the system, and you're not going to be able to forecast what's happening until you understand what's modulating this amplitude. And Western spruce budworm is the exact same. I can take that sweat in a middle inch paper and show you it's the exact same, but just take my word. I've explored this a little more in a subsequent paper in 2024, where I was showing that with these simple panel A is a simple autoregressive model of population fluctuation. And if it's simple, then you basically get these precise forecasts with these narrow confidence intervals on the forecast. And this is not what spruce budworm looks like. It doesn't cycle that regularly. It's a lot more like this. Now, this is a stochastic simulation where I've adjusted the amount of noise going into the system. So it's a noisy oscillation. And now you can see is you've got a massive confidence interval and no ability to predict what happens next. That's a lot like what you get from the historical tree ring data. So maybe it's stochasticity that's driving that, but maybe it's something else. In the same paper, I overlay the eastern and southern Quebec tree ring data, and I show that there's this curious pattern of amplitude modulation. And you'll see why this matters. At first, it's going to seem like I'm out there on a limb, but the eastern Quebec series is the blue series, and the southern Quebec data are the red series. And you can see that the red and the blue are not really all that well synchronized. There are intervals where they tend to peak at the same time, like interval 8 and interval 10, a little bit in interval 9, but there's some of the other intervals where the blue is peaking before the red, 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 blue is peaking before the red. This here, it's not even clear if that's a single cycle or is that 3 subcycles. So the notion of a cycle starts breaking down. And so I wrote this paper about what is a cycle, what is an outbreak, what do we mean when we process these data. But the takeaway point on this graph is that in eastern Quebec, you get this weird pattern of amplitude modulation where it's through the Little Ice Age, you get these low intensity cycles. But the opposite is happening in southern Quebec, where you get high amplitude oscillations during the Little Ice Age, and you get low amplitude oscillations 400 years ago and right now, today. So what's modulating that cycle amplitude? Now that's a pattern I've seen again and again and again over the decades. And I think I know what's causing it, but there's a lot to this. Oh, that I can't see the next panel. The point is, on the next panel, now I build a forecast model and showing that when you sum the two series together, suddenly, whereas you're not able to get a precise forecast with the individual data, when you sum them, suddenly you're able to get a more precise forecast. So there's something offsetting the variability, the amplitude variability that degrades forecastability in the two series. When you sum them, suddenly you get some precision in your forecastability. So something systematic is going on here. It's either climate change, it's a change in forest structure, something systematic is varying that's modulating cycle amplitude. Now, all this was known to me in 2004. I didn't publish it then because I didn't have the words, I didn't have the tools, I didn't have the methods, I didn't have the techniques. But this is all published now. But back in '04, I was like, what are we going to do about these patterns? So we set up this Border Lakes project in the border between the U.S. and Minnesota in the U.S. and Ontario in Canada, and we wanted to look at the dynamics of spruce budworm in this very fragmented multi-species mixed forest. And it's a forest where that's because you have Quetico Provincial Park in the north and you have the Boundary Waters Canoe Area Wilderness in the south. You had this forest harvesting that happened in the 1900s with the removal of early 1900s with the removal of the big pine, but they didn't touch the spruce, they didn't touch the jack pine, they didn't touch aspen. So the white pine was taken out and then it was left to kind of fill right back in because it was horse logged. It filled right back in with fir and aspen. And so this is a quote unquote relatively undisturbed landscape where there's not even any roads. You have to paddle around to get to these sites. So this study was funded in '05. We got the field data in '06 and '07. And then now we've published 3 papers in 2018, 2020, and 2024 that look at the spatial dynamics of spruce budworm in this complex landscape. But we also chose to do tent caterpillar as kind of a double-blind control. Like, it's one thing if you show patterns, host-dependent patterns of site synchronization with respect to spruce budworm, but if you show it with tent caterpillar as well, now it's got a little more credibility. And now you've taken out the climatic factor because you're controlling, because climate is affecting both insects equally because they're both early season defoliators. So if you could show that the change in dynamics is host driven in both systems, you've really nailed it down that host is driving the spatial dynamics. And that is what we show in these 3 papers. So I want to very quickly show you some key results from this series of papers and then show you a little bit more about that and then move on. So these are tree ring studies. So what you see in the on the top frame are the spruce budworm series, spruce budworm tree ring constructions, and you can see the Ontario dominated clusters in black and the Minnesota dominated clusters in gray. And there's 2 slopes computed there, and the 2 slopes cross each other. So budworm outbreaks are becoming more intense in Ontario and less intense in Minnesota. The frequency is about the same. It's a classic 30-year cycle in Ontario, but it's a more complicated cycle in Minnesota. But the point here is the trend. And these trends are statistically significant despite the fact that, this is a terrible way to measure dynamics by fitting a linear trend model to a cycling process. But grain of salt. The point is on the bottom series is tent caterpillar. And so now we've got 6 cycles of tent caterpillar, and in the Ontario series, tent caterpillar is diminishing in amplitude over time and it's rising in Minnesota. So these 2 slopes are also significant and they also cross each other. Furthermore, the budworm and the caterpillar series, they cross each other too. So what does that mean? It means that where the one insect is gaining in importance, the other is losing in importance, and vice versa with the other species. So these things are seesaw cycling in time. There's a seesaw there. And these seesaws are coupled to one another, suggesting that there's something driving the seesaw and the flip in the seesaw in space. And what we showed is that it's forest structure. Okay. Here is on the bottom right is a PCA of 24 different species characteristics, host species characteristics. There's 12 variables, and there's like 12 different structural variables: patch size, percent forest cover, and so on and so forth. 24 variables in a PCA. So PC1 in this PCA, this isn't the PCA, but there's 24 variables boiled down to two PC axes. And here I just plot the PC1 scores. So you can see this blue area, which is the Quetico Wilderness, Ontario, and the boundary waters. This blue area is conifer dominated and high percent forest. This red yellow area is more aspen dominated and very patchy. Okay. And if I take that forest map of the PC1 scores and I compare it to the impacts of the two insects, the pattern is stunning. We were absolutely gobsmacked to see how clear the pattern is, that where it's conifer now is where now for the past 40 years it's been spruce budworm dominated. Or sorry, this is very important that I get this very right. Where it's conifer dominated now, that's where now you've got spruce budworm heavy impact. That's the red to yellow heavy impact. But 4 decades before, from 1928 to 1977, budworm was not there. So this is the budworm changing places, going from Minnesota in the south into Ontario and the northwest. Okay, and tent caterpillar is doing the exact opposite. It used to be up in Ontario in the northwest, and now it's down around the periphery of this whole study area, especially in Minnesota and Ontario. I said Ontario West, I meant Ontario East, and in Ontario West. So the correlation between insects is 0.7 on the diagonals and minus 0.5 around the frame. And it's about 0.5 between the insect and the forest. So modern day forest structure measured in the past 2 decades is determining where the insects are distributed. The insects are cycling most intensely where their host is located. Okay, kind of a complicated thing, but it's simple and it's intuitive. Happily, where there's host, there's insect. But we need to be clear that both insects are across this entire mixed landscape. We are not talking about like 100% fir versus 100% aspen. It's like 40% fir versus 30% aspen. It's a very mixed landscape. So the slow dynamics, okay, this shows that the slow dynamics are modulated by forest structure. But even the fast dynamics are modulated by forest structure in the same way that I showed you for tent caterpillar in Alberta on that little grid. In this big area that's 200 kilometers by 200 kilometers, we get the same patterns, complex patterns of eruption pulses that are localized. They never cover the whole area, and they tend to be focused on one part of the landscape or the next or another or another or another, always moving around in this systematic pattern about the landscape. For both spruce budworm, so this is plot deals with spruce budworm, and so I'm looking at the distribution of spruce budworm eruption pulses in like small time windows now, about 10 to 15 years. Okay, and so these budworm forest correlations are sometimes negative and they're sometimes positive. This is because the outbreak is moving around between in this PC space from the high spruce fir forest, high fir forest, and high percent forest, PF percent forest. The blue, this is the boundary waters and Quetico versus Minnesota south, where it's aspen dominated. There's lots of hardwood, lots of maple, lots of aspen, lots of cover diversity, lots of edge density, and high area weighted mean patch size. This is a complex landscape. This is more a traditional conifer landscape. So the outbreak is moving around in a systematic manner, and the forest structure is serving as a powerful axis of desynchronization to the cycling system. This is not consistent with clockwork theory. And it's the same for tent caterpillar, although now it's more PC2 that's driving the pattern of bimodal correlations between where the insect is and what the forest attributes are where the insect is. So now these blobs are tilted a little bit because it's now more centered along PC2. So whereas it's species differences that are driving budworm, it's structural differences that are driving the outbreaks, where the outbreaks occur for tent caterpillar. But it's qualitatively the same result. Forest structure is serving as a very powerful axis of desynchronization, which is what I showed in Alberta with the tent caterpillar. So the results are starting to mount now that something weird is happening in this system that's not consistent with the Tomoyama the British school, the clockwork theory. Something weird is happening and something bottom-uppy is happening. And so the concluding slide for the border lakes is this. If the slow dynamics and the fast dynamics are modulated by forest structure, well, why not all time dynamics? Maybe the intermediate dynamics are, and maybe the very long-term 100 scale, 200, 300, 400-year dynamics are also modulated by forest structure. Also, if this is happening in Ontario, Minnesota, well, why wouldn't this also be happening in places like Quebec and New Brunswick and even British Columbia for that matter, extending the analysis out. The point is that forest structure, it's the X factor that a lot of traditional foresters and historical foresters in Quebec said that it was. But the British school tended to poo-poo this and emphasize the top-down role of parasitoids in driving a host parasite, a predator-prey cycle. Okay, so host matters, bottom-up matters. And in this recent manuscript that I put together with the help of Alan LaRocque, the host of this talk, we decided to do something really stupid, which is once you get a really cool result with two systems, what happens if you look at a third system? Do you get, additional evidence? And so we looked at the spatial temporal dynamics of jack pine budworm in this landscape, where there's only about 7% jack pine in this very spruce fir aspen landscape, and we found nothing. We found we almost couldn't see the outbreaks. They were so weird. So we found this result in 2006, and we thought, well, there's nothing there. There's no there. And I started taking a look at this when I was in Victoria last time, talking with Alan over the days, Alan LaRocque, and we decided that I would compare the spatial temporal patterns in our border lake study area, this big bubble in northwestern Ontario and northeastern Minnesota, and we would compare to this very small area, Spruce Woods Provincial Forest in Manitoba, where there's a ton of jack pine, and where these guys in 2015 had said, oh, jack pine budworm are cycling synchronously in our study area. Well, they weren't cycling synchronously in our study area, so what gives, right? So we took our data, our raw data. So the Border Lakes is the green series over time, and the yellow is their series in Spruce Woods. And the two series look very similar. In fact, they're very highly correlated with one another, which is not too surprising. Trees are doing the same thing, even though they're separated by 600 kilometers. They're doing kind of the same thing. And you can do fancy autocorrelation and partial autocorrelation analysis, panels B and C, a spectral analysis. You do these time series analyses, and they show, hey, the data are kind of doing the same thing. So, there should be no difference. Yeah, but when you take the raw data and you run them through the processing methods that these guys did in this 2015 paper, and that Swetnam and Lynch innovated in 1993 with Western spruce budworm on Douglas fir, use the exact same method, and you get a stunning, remarkably different result. The curve on the left is in the Spruce Woods Provincial Forest, where you have 70% jack pine, and panel E is the time series behavior in the Border Lakes with it's green and it's only 7% jack pine. And you don't need the time series analyses on the bottom to show you guys that this system is cycling with high correlation of 0.52 correlation between the gray time series, and the intensity of the cycles is pretty high. You're getting about 40% during the cycle peak. 40% of the trees are showing some impact. Sometimes it's as high as 80. Well, in the Border Lakes, that's not what you get. The mean pairwise correlation between the gray time series is 0.15. So it's like a third the magnitude over here in Spruce Woods, Manitoba. So these gray lines are all over the place. And when you sum them together, the mean percent of trees affected PTA never rises to more than 30%. It's typically around 10, 15%. So people wouldn't even call these outbreaks. So what are they? They're like these kind of periodic endemics that are incredibly poorly synchronized across the Border Lakes landscape. So in other words, host abundance is driving cycle amplitude and cycle synchrony when you contrast these two systems. You don't see it when you look at the big, beautiful green data set, but when you extend your study area to include other areas that have tons of pine, now you see it in the contrast. So our study area would need to be 600 kilometers by 600 kilometers to see this, which would cost like $1 billion instead of the $7 million that we spent. So this led us to this idea in this 2025 paper that the dynamics of the system, and this is taken from a Halling Walker paper from 2001. showing basins of attraction for forests and pests in complex landscapes. So you've got this spruce fir, spruce butterworm attraction basin, and you've got an aspen tent caterpillar attraction basin, and off to the far right, you've got this jack pine budworm attraction basin. And so the idea we have is that these attraction basins get bigger or smaller and more attractive or less attractive depending on how much host there is in the landscape. So it turns into a great big attracting black hole if there's a lot of host. But if there's not a lot, like for jack pine budworm, the insect might get into that basin of attraction, but it's easily kicked out of it. Okay, so this is pretty significant. What this is suggesting is that Holling's resilience concept is not just a metaphor, it's an actual model. It's what actually governs the system dynamics. So we have gone now from the British school of population cycling theory all the way to Holling's idea of complex ecosystems with resilient dynamics, with multiple basins of attraction and alternative stable states. And the accessibility of those stable states is determined by host forest landscape structure. Okay. I don't even have a timer on. How many minutes am I at, Alan? Anyone? No. I didn't even click a timer. I don't know where I'm at. Um,
I think it's about 7:45.
Oh, thanks, David. I was muted. Yeah. You were about 40 minutes in, Barry.
oh wow. Holy cow. That's a good introduction. Um, there's another component where at this point I wanted to migrate from kind of tree ring data to foliation data to population data. I have a whole other sequence to show you. But basically, this is a good place to kind of make that transition, showing that the clockwork theory on the top is Rayama's model is not supported in the spruce budworm model, jack pine budworm, forest ant caterpillar. There's really much stronger support for the bottom-up ideas of Rene Thom, Kenneth Watt, Don Ludwig, James Murray, A.C. Fowler, and of course Holling. The bottom right, the blue, the UBC school, the Institute of Resource Ecology. So these ideas map pretty much to the British school versus the UBC school. Okay, so I find myself nowadays very much favoring the kind of UBC perspective on forest insect interactions. And I'm not even going to show the details here, but I want to show you that there's been a century of debate about which of the two ideas is right. Okay, and ideas have waxed and waned over time. So this is 100 years of arguing. Okay. And this is in our 2015 paper that I did with Brian Sturdivant. And in that same paper, we showed that, look, the UBC school, they have their model. Rayama has his model. And even though the models are different, structurally, there is a basis for comparing them. The difference is that the bottom-up model is bottom heavy. The blue is bottom heavy. There's a lot of terms in the model in blue. Rayama, the blue is a single parameter. The top-down is very heavy in Rayama's model. That's the red. Whereas it's just a single piece of an equation in the Ludwig et al. Model for spruce budworm. So these models are reconcilable as long as you can get the top down and the bottom up working together. So we kind of said this in 2015, and the Border Lakes experience is bearing this out. The jack pine budworm data is bearing this out. Okay. The second part of the talk, which is what I'm going to skip over, is how if we start looking at population data for spruce budworm, we see that, and Renier was my master supervisor. He's been a convert to basically the UBC school of thinking through gathering data and showing that there are these positive density-dependent effects. In a 2007 paper, in a 2013 paper, and in a 2019 paper, increasingly Jacques has moved away from Rayama, has moved away from the British school, and has embraced UBC school thinking. And we did this paper when we realized we were on the same page in January 2013, last October, it was just 1 year ago, we got together and we wrote this paper. And I'm not going to present the paper, but it centers on Rayama's curve in the red box, and then this other curve by Solo et al. 2003. And a long story short, when we go through this analysis of the data, we basically see that spruce budworm is doing what Solo said. It's not doing what Rayama said in anywhere in Canada. Anywhere you look with population data. Okay. The positive density dependence that Renier reports is the exact positive density dependence that Campbell reported in 1993 in that paper that I slammed down on my desk and said, this is garbage. This has got to be wrong. I slammed it down in a kind of a Royamian fit, like, oh, this can't be right. Well, Campbell was right. And this positive density dependent relationship is what drives outbreaks in Western spruce budworm, and it's driving them in Eastern spruce budworm too. And this goes way back to Watt 1963 and Morris with the Green River data starting in 1947. These guys said recruitment is a hump shape. This is where outbreaks come from. And Royama said it's not. And now, kind of 2025, Jacques and I have come full circle, and we agree with Campbell. This is what's happening in both the spruce budworm system and the Western spruce budworm system. And in fact, if you read papers by myself and Alan Carroll, it's the exact same model that is driving mountain pine beetle dynamics in British Columbia and is driving the dynamics that Hector Allen Richmond talked about in Forever Green. Okay, so the big kind of takeaway is when I go through the Royama's, there's elements of his hypothesis that have merit, but it's overall the BC school is winning this race. Which takes me to my final slide, showing you how important the UBC perspective in the blue box, all these names, all these people, you can't make sense of cycling forest insect systems like Eastern spruce budworm, Western spruce budworm, name your budworm, until you understand how the UBC school perspective bears on the British school's perspective, their elegant theory of population cycling. And I didn't say anything about Judy Myers and Neil Gilbert, but there's this beautiful little paper in the British Entomological BC Entomological Society in 2001, where she lays out the importance of Gilbert and Halling to the whole BC entomology paradigm. It's a beautiful little paper, and it really pulls all. It's the final piece of this slide, and so I conclude by saying, I basically. Have I gone through a religious conversion? No, it's not religion, but I've gone through a real evolution in my thinking on this system, these systems. And I see the same thing happening in all these systems. That's it.